So let's start the next module where we'll talk about what is a latent variable. How many of you have had exposure to latent variables in some course or something before? Okay, okay, very few of you. Okay, okay. So let's see. So earlier what we said is that the neighboring pixels in an image are actually dependent on each other. Right? That's what our Markov network was. And we kept the definition of neighborhood to be vague, whether it's just the left, right, or top, bottom, or diagonal, or even 2 rows and 2 columns. Right? That's all up to us to decide what kind of neighborhood we want to choose. Okay. So why is it so? Why do we say that the neighbors of a pixel are dependent on each other? Because we expect the color, texture, etc. to be the same for the neighboring pixels. Right? That's the idea. So let us probe this intuition a bit more and try to get some reasoning into why this actually happens, right? So we'll take an example that suppose we ask a friend to send us a good wallpaper, and he or she thinks about it and then sends us this wallpaper, okay, this image. So why are the pixels in the top portion of the image blue? Why? Can you think from the friend's perspective? Because he or she thought that it would be good to send us images which contain a sky as opposed to mountains or green fields or various other possibilities, right? Why is the sky blue and not black? Because he or she thought that it's good to send an image of daytime as opposed to nighttime, okay? Okay, fine, then why is it not cloudy? I mean, it's a bit cloudy, but why not completely gray, or, I mean, you can't even see any of the blue color. Why not that way? It's fine to send images of sky. It's fine if you want to send daytime images, but why not cloudy? Well, again, he or she made this decision that I want to depict a sunny day and a clear sky as opposed to a cloudy sky or something, right? Are these decisions known to us? What do we observe? Just the image, right? But these are some inherent decisions that the friend would have actually taken. Right, that I want to send, and these decisions could differ, and there could be a very different explanation for why this image was sent to us, but there was some underlying decision which led to this image, and we don't have access to that decision. We just see this image, and what we observe is just the pixels. We don't have access to these underlying decisions that were taken, and I think all of us agree that there was some underlying decision which was taken, and decision could be as simple as randomly pick an image, right? That could also have been there, but there was some decision which led to this image being generated, right? So that's the idea that I'm trying to emphasize on, right? We only observe the images, and these decisions are hidden from us. We do not really observe them. So what exactly are we trying to say here? So we are saying that there are certain underlying characteristics which not only determine the pixels, but they also determine the interactions between the pixels, right? So now suppose instead of a clear sky, if the friend had decided to send us that image of Taj Mahal which we had seen in some of the earlier lectures, right? Then the sky was not so visible, the Taj Mahal was covering most of the sky, right? So the background was very little in that case. So in that case, the interactions between the pixels would have been different. The dome would have interacted with each other. It wouldn't have interacted with the sky and so on, right? So these latent decisions actually determine how these pixels are going to interact with each other, right? And what we could do is, we could think of these additional, latent decisions, right, as additional random variables in our joint distribution. So what do I mean by that is that someone decided that of the two possibilities, sunny or cloudy, I would set the value to sunny. It was a random decision, right? Someone decided that instead of daytime versus nighttime, I would pick it as daytime, right? So this is same as high-low kind of examples that we are doing, right? Again, someone decided that the color should be of certain type and so on, right? So these are additional random variables on which certain decisions were taken, and then we saw these observed images which again contain random variables, right? Because I have decided I want to plot a sunny image, but still there are several ways in which I could have arranged the pixels to get a sunny image, right? I could have not just a sky, I could have a sky with something in the foreground and so on, right? So despite taking these decisions, there's still a randomness in what you will observe, and you could see different images of, say, sunny sky with green fields and so on, right? There could be so many images of this particular description, okay? So These are latent because we do not observe them. What we observe is only their effect, which is in terms of the pixels that we actually see or the images that we actually see. Fine. So more formally, what we have now is, earlier we just had these observed variables which were V. We have been calling it X, but now I'll just change it to V and H, V for visible and H for hidden, right? So we had these observed variables 1 to 1024 because it was a 32 cross 32 image. And now in addition, we are saying that there are some hidden variables H1 to Hn, okay? Now can you think of a Markov network to represent the joint distribution P of V comma H? First of all, is this question valid? Can I ask you to think of a Markov network? Yes, right, because this is irrespective of whether I call it V comma H or just collectively call it all of them as X. All we have at an abstract level is a bunch of random variables, and I'm interested in learning their joint distribution, right? And since this was images, and we have already made a case that in the case of images there are no directions, it's just the affinity or the interactions. So that's why I'm asking for a Markov network as compared to a Bayesian network. That's again a modeling choice which I have made. I've assumed that these are not, the pixel interactions are not dependent on each other. In the sense, there's no direction there, they're just interactions, okay? So this is a valid question. Now can you think of a joint distribution for this? And what I'm asking for you is think of a factorization. Or first let's think about the graph. If H was not there, then what was your graph? If H was not there, what was the graph? All the neighborhood pixels depending on each other, right? So this is the graph that we had earlier, right? And again, the neighborhood is a bit vague. We can define it the way I want, and here I am considering the diagonal neighbors also, okay? Now, since that you have H, and I was trying to make a case that these pixels are what they are because someone decided or made some decisions on these latent variables, right? Now convert that first to a probabilistic argument that what depends on what, and once you convert that, then tell me what the diagram would be or what the graph would be. How many of you get the setup? Like how many of you get the question that I'm asking you? Isn't that a bit over-specified? You said something plus something, right? Are both those things required? Think in terms of parents or Markov blankets or things like that, right? Think of it this way. If the first two pixels are blue, and I know there was some latent variable which was sky or sunny, do I need to make these two pixels dependent on each other given the latent variable? So he said that your cliques would be, that's one way of answering this question, the cliques would be these 9 pixels that you see here, and in addition you'll also have all of these 9 pixels connected to the hidden variables. That's what you meant, right? And I asked him that, isn't this over specified? You said that it's clique plus something, do you need both these terms? And then I sort of gave a hint or I just made a statement. So now concerning all of this, tell me what the Markov network would be. So he said bipartite graph. What are the two partitions? H and V, that's easy to answer. So what would you have? Now, given that's the answer, can you reconcile with everything that we have discussed? Does that make sense? That, what does it mean? Since it's a bipartite graph, what does it mean? And you said the two partitions are H and V. So do you have connections between the V's? So do you have the cliques that you see here? No. Do you have connections between the H's? No. So what are the connections that you have? V's and H's. So some H's connect to some V's, or all H's connect to all V's, or what's the assumption? All H's connect to all V's, right? Even if you look at the example which we were discussing, the toy example where there were only 3 latent variables, which was sky, sunny and daytime. Every pixel depends on all these 3 values, right? If I change any one of these, the pixel will have to change, right? So in that case, it has to be a fully connected thing. Yes, so then you could think of additional random variables. There could be one random variable which says that how many clouds are there and what's the size of each cloud, big or small or something. This is a bit vague at this point because, see again, and I'm going to come back to that point. There's a reason why we call this as hidden variables, because we are not going to observe them in practice, right? These were decisions taken by our friend, and I'm going to make the assumption that you can't even ask the friend, right? So that we will never know what these decisions were. This is only for the purpose of explanation, and later on I'll come back and say that, okay, all this cloudy, sunny and all was just for explanation. In practice, we don't really know what these hidden representations were. And I'll also make a case that something like this we've already argued in the course before, that we don't know what these hidden representations are, okay? So then probably the story would become clear, okay? But that's a fair doubt, and ask me again if it's not clear after the next 10 slides or something. Okay, so this is what the Markov network would look like. Of course, from some pixels I have not drawn the edges, it would just become too complicated, but just imagine that all these edges are also there, right? So every visible pixel is essentially connected to every hidden pixel. So that's the correct answer. It's a bipartite graph. And the reasoning is that once you know the hidden variables, that completely determines the interactions between the neighboring pixels, so you don't need to capture them again. So, I mean, just try to visualize the way you are comfortable, either in terms of a Bayesian network, where given the parents, you are independent of, the siblings are independent of each other, or in terms of a Markov network, where given the Markov blanket, which is all these hidden variables, you are independent of all the other visible pixels. In either reasoning, it should be clear that the visible pixels are independent of each other. How many of you get this? Okay. And this is the intuition that we were trying to build on the previous slide, right? That these are some decisions which have been taken by someone. It doesn't matter that we don't have access to these decisions. It doesn't matter that we don't know what these decisions are, or we don't even know the definition of these random variables, right? I don't know whether the first random variable is actually sunny or day or cheerful or happy or what. I don't know these. It's just that there are some latent variables, and my final observations are based on these latent variables, okay? So let us probe this idea a bit more, and we'll try to talk about this idea in terms of two concepts. One is abstraction and the other is generation. So let's see what that means. So first, let us talk about abstraction. So suppose we have learned the joint distribution P of V comma H, okay? And this should be obvious that given this joint distribution, I can compute this P of H given V, right? In particular, I could compute for a given V, I could compute the hidden state which maximizes the probability of P of H given V. What's the English way of saying that? In terms of the decisions made by our friend, right? Given an image, I can actually assume that the joint distribution is given to you, right? So if I can compute the argmax of P of H given V, what am I actually computing? The most likely hidden decisions which the friend had made to give us this visible observation, right? Okay? Fine. So, as I said, that the most likely decisions that were taken, and at this point, I'm keeping all the computational problems aside, right? Whether this joint distribution is tractable and all those things, I'm keeping aside. I'm just assuming someone has given to you and you have infinite compute power to compute this, then this is what it means. So what does H capture? Now try to relate it to other things that you have done in this course. What does it capture? H should give it away, right? What does H capture? It captures some abstract representation of the image, right? Fine. And still there are some things missing here, but we'll get there. Okay. It captures an abstraction of the image. Now under this abstraction, what would happen to images? Okay, so let me ask you this. So this abstraction is capturing the important properties of the image, right? So what do you expect to happen to images which look very similar? The abstract representation would be very similar to each other, right? So for example, right, if you were to describe this image to someone, you wouldn't say that I'm looking at an image whose pixel 1 is blue, pixel 2 is blue, all the way up to pixel 1024 is beige. This is not how you're going to describe it. How are you going to describe this image? I can see everyone imagining and dreaming and so on, but yeah, let's assume that you're not going to get there anytime soon, but still describe it. It's a sunny beach with an ocean. I don't know why it's an ocean, but in the background, and beach sand, right? Instead of white sand. That's an abstract representation of this image. That's how you would abstractly describe this image. The 1024 pixels are too dense, right? That's a very over-specified description of the image. You're not interested in that. We're just interested in this abstract representation. And this is the kind of abstraction which we expect H to capture. Okay, again I'm building this up, saying that H will capture all this, and then I'm going to play it down later on, but I'll do justice to it when I play it down, right? I'll relate it to something that you have already seen, okay? And now under this abstraction, what would happen to all these similar looking images? They would all have a very similar representation. On a per pixel basis, are these images similar to each other? They're very different orientations of the beach, and like they are different, right? I mean, let's not just get in. They are just different, right? On a per pixel basis, if I take the squared difference between them, they would be different. But under this abstract representation, what do you think they are? They are very similar. And we are always interested in these abstract representations because that captures the important properties of the image that we are interested in or the data that we are interested in. Have you done something like this before? The correct answer is throughout this course, right? I mean, deep learning is deep representation learning, right? The right term is deep representation learning. So we did this in autoencoders. We did this in multi-layer perceptrons, right? We said that every layer captures a different abstraction of the image. We did this in convolutional neural networks, where every layer of the convolution neural network captures a different abstraction of the image, right? And so now let's, this is very similar to the idea behind PCA also, right? Now that is where now I'm going to play it down a bit. So we still need to figure out a way of computing this P of H given V, right? We still need to find out that if I give you an observed image, how do you compute the argmax H, which is the most likely hidden configuration which generated this image, which is the same as saying that what's the most likely hidden representation for this image. In the case of PCA, this boiled down to learning the eigenvectors of X transpose X. In the case of autoencoders, where you again learn this abstract representation, what did it boil down to? What was the learning that you did there? What did you learn there? Nothing? These sudden blackouts are completely inexplicable. What did you learn in autoencoders? Hidden representation, but what? So in the case of PCA, you learn the eigenvectors of X transpose X. In the case of autoencoders, what do you learn? The parameters of the network, right? The parameters of the encoder and decoder. Come on, right? W encoder and W decoder. And we still, but now the analogy here would be, what do we need to learn here in this case? The dash of the joint distribution. The parameters or the factors of the joint distribution. And we have still not seen that. We are far from it, but we'll get there eventually. Once we know that, we have the answer to the first bullet. We can compute P of H given V, right? And that is again the motivation for learning a joint distribution, because once you have the joint distribution, everything else can be done from that, right? All sorts of questions that you want to ask about those set of random variables, you can compute from the joint distribution, right? So we have still not seen how to learn that, but there's an analogy. You have seen it in PCA, you have seen it in autoencoders, and we'll see it soon or in a few lectures before this course ends, how to learn this joint distribution, okay? Right. So I'm going to drag this a bit more. So in practice, we have no clue what these random variables are, what these latent variables are. As I said, you're not talking to your friend, you're not really asking him or her what was the decisions which led to this particular image, right? And in fact, there could be many explanations for that. But this is not something new. This is exactly what we saw in PCA also. In the case of PCA, the original dimensions of the data had some meaning, that the first dimension is weight, the second dimension is height, the third dimension is salary and income tax and all those things. But once you transform the data into a new space, those dimensions had no meaning, right? You cannot say that the first dimension corresponds to a certain thing or the second dimension corresponds. You cannot attach labels to these dimensions. All you know that these are dimensions which are independent of each other and they have a high variance around these dimensions. Those were the wish lists that you had for PCA. The same thing is true for even autoencoders. When you learn an abstract representation for the autoencoder, your original data had certain semantics, but once you get the hidden representation, you just know that it's a 100-dimensional representation. You don't really know what each of these 100 dimensions are there. And the same thing applies here. You don't really know what these latent variables are. You just know that there are some latent variables. Just as in those two cases, you knew that there is a certain hidden representation which is able to represent my data better. Even in this case, you know that there's a latent representation which actually gives a more succinct representation of the image, but you don't really know what are the semantics of this latent variables. All you know that maybe all images come from a 100-dimensional space instead of a 1024-dimensional space. Once I have this 100-dimensional values, I can capture everything that is there in the image. And that was the idea behind PCA, that was the idea behind autoencoders, and that's the idea behind this particular structure. This latent variable is capturing the essential semantics of the image, right? Even though we can't really identify what these variables are. Okay, so this is not something new to this is what we have been dealing with throughout the course, okay? Only for illustration purpose I have been saying that this is sunny, this is cloudy and so on, but that's just for explanation. None of these variables have any meaning, okay? Is that fine? And actually, it does not even matter, right? Because it could have happened that even though our friend did not tell us his or her decisions, he could have thought of something very different. Maybe the image was of a beach or sunny or so on because they wanted to convey something which is cheerful or romantic or something else. Right? These dimensions could have taken some very, very different values than what we thought they are, but it doesn't matter. As long as there are some latent variables such that under this latent space, similar images become similar or have a very similar representation, then we are fine with that. We don't really need to actually define these latent variables. Right? I know I'm repeating myself, but it's very important that you understand this concept. You can say things about visible variables that this is pixel 1, this is pixel 2 and so on. You can't make these arguments about hidden variables. You can just say that there's a latent space which captures the semantics of the data. Okay? And again, I emphasize this is not something new which I'm just throwing up at you. This is what has been our theme throughout the course, whether in autoencoders or convolutional neural networks or any kind of multi-layer perceptrons, right? Okay. So how do we learn this? So what is the question that I'm asking? How do you learn this, right? So I'm going to keep a track of all these questions, which I'm going to say that we'll get there eventually, and all these questions will essentially be saying the same thing, that how do we learn this joint distribution H comma V. So I'll keep asking these questions and I'll say that we'll look at it eventually. You'll find that there are many questions which I'm saying which we'll see eventually, but this all boils down to one single question, which is how do we learn this joint distribution. So you already saw one question where I say that we are far from learning it, and that was how do we learn this joint distribution. This again, where I'm asking how do you get the hidden representation, again boils down to how do you learn the joint distribution. And once you have the joint distribution, inference is straightforward. Right? Now this was about abstraction. Now let us talk about another concept related to latent variables, which is generation. Okay. Once again, assume that we are able to learn the joint distribution P of V comma H. Now from this distribution, I can find the following thing. I can find R max V given H. Now in English, what is the question that I'm asking here? Given a hidden representation, generate an image which adheres to this. Why is this interesting? Just think about this for a minute. I'll give you a few hints. You had a large amount of data, and let's say all this data were about scenic pictures, right? And mainly say skies and oceans and green fields and so on. From this data, you have been able to learn P of H given V, right? That means for a given image, what was the abstract representation that led to that image? Okay. From this data, you have been, if I give you any image, you can give me a H for that, the vector H for that image. Now I'm asking you the reverse question. That you can also do this. You can also do P of V given H. Now, given that you can do this, I want you to be creative enough to give me a good use case for this. Yeah, that's probably okay. But I ask you to be a bit creative. Reconstruct from a distorted image. Yeah, that's fair. For some other ML problem. No, I mean, I've given that skies and beaches and so on. Now my other ML problems, I want to classify cats and dogs, the hottest problem. How will I do that from here? So suppose this image, which is not visible, right? You have done training, everything is over. Somehow you have figured out how to learn this joint distribution. Now you can actually compute an H for this image, right? Wouldn't you be interested in knowing that if I perturb this H a bit, what kind of an image will I get? You want to generate, this is an image of a sunny beach, say. You want to generate other images of sunny beaches. You take the hidden representation of a sunny beach, just perturb it a bit and see if you get a different kind of a sunny beach. Does that make sense? Does that make sense? How well you can do it depends on how much data you have, how effective your learning was, whether you actually learned the parameters well, right? So you can't give me 100 images of sunny beaches and say that, okay, now go and generate 1,000 more. That won't happen, right? I don't even know what's the right number, whether it's 100 or million or 10 million or 100 million, I don't know. But asymptotically, right, if you had enough data, can you actually do that, right? So that's what people are interested in. That's one of the hypes around AI, right? So this creative AI, that can you create, and now I can extend this to many things, right? Suppose I learn a joint distribution of poetries, right? Now you can imagine hidden variables for poetries also, right? It could be tragic, romantic, or it could be about nature, philosophy, or so on and whatnot, right? Now, given a lot of poetries, if I can learn a joint distribution between these hidden variables and poetries, now take some poem, get the hidden representation of that poem, and now try to generate other poems which look like that. It's all still slightly science fiction-ish. It's not that this has been solved and people are doing this very, very well, but people are doing it to a certain extent, which is appreciable, right? So it's not that it's been solved, but at least there is a scope for being creative by doing these things. So once you learn a joint distribution, so essentially you're trying to learn how do people create images, or how do cameras click images and so on. And now given these things, can I create more images? Can I create more text and so on, right? So that's one of the goals which are being pursued right now, okay? So that's the overall context of why you need this generative model, right? So generative model actually tells you how was the data generated, so that if needed, you can generate more data of that kind, right? So that's the overall bigger picture that you have here. So this is what I can say now, right? Create an image which is cloudy, has a beach, and depicts daytime. This is in English. In the vectorial sense, I would say that take this hidden representation and give me another image which could have generated from this hidden representation. Or compute the hidden representation from a certain image, perturb it a bit, so that maybe cloudy becomes slightly cloudy, or more cloudy, less cloudy, or something like that, and then generate new images from that. Even without actually knowing what these hidden variables are, can you still do this? Yes, you can, right? Because you have the visible image, this is the hidden representation for that. All I'm asking is to generate more stuff which adheres to this hidden representation, right? Without actually knowing the semantics of this hidden representation. Everyone gets this, everyone buys this idea that you don't need to really know the semantics of the hidden representations. Please raise your hands if you do that. Okay. So this is what I would give, right? I would give it a vector, not the text description. I would give this vector to it, and I'll ask it to generate. So again, we'll come back to this later. It's again the same question. Once we answer what we can do with P of V comma H, how we learn this, all these questions will be answered. You can keep a track of these things which I'm saying we'll do later if you want. And if I forget something, let me know, but I'm pretty sure we'll cover everything. So, okay, so the story so far has been that we have tried to understand the intuition behind latent variables and how they could potentially allow us to do both abstraction and generation, right? And both these are interesting concepts. Abstraction we have been doing throughout the course, and we have kind of convinced ourselves that it could give us better representations for the data, which could eventually lead to better predictions on that data, right? That's one thing. And we'll now try to concretize these intuitions by developing some equations or models which allow us to capture all these things and the corresponding learning algorithms. Well, whenever we introduce equations, what are we going to introduce? Parameters. And then once we introduce parameters, we need certain learning algorithms to learn that, right? And of course, this is a course on deep learning. We have to tie all of this back to neural networks, right? We have just completely deviated from that. We're just talking about random variables. So we have to stop this randomness and get back to deep learning, right? Okay, fine. So for the remainder of this discussion, we'll assume that all our random variables or the visible variables take on Boolean values, right? So V is a vector from 0 to 1 raised to n. And similarly, all our hidden variables also take on Boolean values. Again, it's 0 to 1 raised to m. So we have n visible variables instead of this 1024 that I've been talking about, and m hidden variables for the remainder of this description, right? And at some point, I'll also say that I'll use x to denote v comma h together, right? So when I want to refer to them collectively, I'll just call them x. So x is again a vector of random variables.